Hello everybody and welcome to Lab 3 of the Qiskit Global Summer School 2021. I'm Anna Fan, a quantum researcher and education developer based in Melbourne, Australia. And in this lab, we're going to be learning how to implement quantum feature maps, quantum kernels, and quantum support vector classification in Qiskit. We're going to be taking it step by step. So the first step is we're going to be introducing the data we're going to use and pre-processing it to be able to be used in the quantum support vector classification. So what we're going to be using today is a small subset of the well-known handwritten digits dataset, which is available through Qiskit-Learn. And we're just going to be aiming to differentiate between 0 and 1. So here is what the 0 and 1 of the dataset look like. So you may notice that each data point is a 8x8 image of a digit, and this is stored as values in an array representing the grayscale of each of the pixels, where 0 is white and 16 is black. So just like in classical classification, we're going to need to split the dataset into training and testing samples. To improve the accuracy of our algorithms, we're also going to be normalizing and scaling the data between -1 and 1. And then to be able to run it on a quantum device or simulate it on our laptops, as the case may be, we're also going to be reducing the dimensionality of the dataset from the 64, that's 8x8, to 4. So note that in Qiskit, this is actually already done for you for this particular data set in this package here. And it's also done for many of the other scikit-learn data sets. But I'm going to be making this explicit in this lab for future reference for those of you who are interested in using quantum support vector classification on your own data. So here we go. We're going to split the data set into sample and testing data sets. We're going to be reducing the dimensionality using principal component analysis. We're going to be just using the standard Python scalars to normalize it and to rescale it, and then selecting our number of data points for training and testing. And so here is an example of a data point. So you can see that all the numbers are between -1 and 1, and you can see the labels, whether it's a 0 or a 1. So to do quantum machine learning, we need to encode the data. We need to take our classical data and encode it into a quantum state. This is done through the use of a quantum feature map. As you have heard in the lectures, the choice of which feature map to use is very important and may depend on the given dataset we want to classify. Here we're just going to look at the feature maps available in Qiskit before selecting one and customizing it to encode the digits data. So as the name suggests, a quantum feature map is a map that takes a classical feature vector to a quantum state, a vector in Hilbert space. This is facilitated by applying a unitary operation on the initial state, where n is shown here, where n is the number of qubits being used for encoding. The feature maps currently available in Qiskit, that's the Pauli feature map, the ZZ feature map, and the Z feature map, are those which are introduced in this Nature paper published in 2019 by members of the IBM Quantum team. And in particular, they point out that the ZZ feature map is conjectured to be hard to simulate classically and is also can be implemented as short depth circuits on near-term quantum devices. So this is what the Pauli feature map is defined as in Python, and this describes a fairly complicated looking unitary operator of depth d. So I'm just going to break this down into pieces. So you can see this equation here shows that we have a layer of Hadamard gates, which are interleaved with these entangling blocks described by this U here, whereby this U, the P denotes the Pauli matrices, hence the name Pauli feature map. The S describes the connectivity between the different qubits. And by default, we have a data mapping function shown here. So this may still seem a little complicated, so let's plot out some examples of the Pauli feature map. So when k equals 1 and p0 equals z, this is actually the z feature map. So the equation describing that unitary operator is shown here. The function in Python of the z feature map is shown here. And then we're going to create a z feature map with feature dimension 3 and 2 repetitions. So what does this look like? We've got our 3 qubits, one for each of those feature dimensions, and we have 2 layers of interleaved Hadamard gates, and these Z rotations based on the data. So we're looking at here the 0th, the first, and the second feature dimension of the data. So note that there are no 2 qubit gates in this particular feature map. This actually means that this feature map is simple to simulate classically and will not provide any quantum advantage. Let's look at a slightly more complicated example. So when k equals 2 and p0 equals z and p1 equals zz, this is actually the zz feature map, the unitary operation described here, and the Python function shown here. So let's create one for dimensionality of 3 with 1 repetition. So we can see the layer of Hadamard gates. We see the first layer of Z rotations, and then we see the ZZ rotations with the data mapping function between them. So you see the pi minus the first data point and then pi minus the second data point multiplied together, whereas here we just saw it was the data point itself. So now that there is entanglement in this feature map, we can define the entanglement map. So by default, this is full entanglement, but we can also have linear entanglement as well as circular entanglement. Obviously, these will look more obviously different if there are more qubits. So we can also customize the Pauli gates used in the feature map. So for example, if P0 equals X, P1 equals Y, and P2 equals ZZ, this is the description of the operator. And here is how we define it in Qiskit. And then this is what it looks like drawn up. So we see here the X, P1 being X, and then we can see the P2 being Y, and then we see, P1 being Y, and then we see the P2 ZZ. And we can also customize the custom data mapping function. So you saw before we just had pi minus x1, pi minus x2 multiplied together. So here, for example, we can add a sign to that value. So this is the definition of that custom data mapping function. And here we define a Pauli feature map using that custom data mapping function there. So they are the Pauli feature map, the Z feature map, and the ZZ feature map. There are also the nlocal and the 2nlocal functions in Qiskit's circuit library, which can be used to create parametrized quantum circuits, which we can use as feature maps. So here is a definition of both of these functions in Python. So both of these functions create parameterized circuits of alternating rotation and entanglement layers. And both layers, the parameterized circuit blocks, act on a circuit in a defined way. The rotation layer, the blocks are stacked on top of each other, while the entanglement layer, that depends on whether it's linear or full or circular. Each layer is repeated a number of times in the number of repetitions. And by default, a final rotation layer is provided unless you tell it to be skipped. So in n-local, the circuit blocks can be arbitrary sizes, as long as it's smaller than the number of qubits in the circuit. While in 2-local, the rotation layers are always single qubit gates applied to all qubits, and the entanglement layers are only 2 qubit gates. So what does this actually look like? Here is a 2-local circuit with Ry and Rz gates in the rotation layer and Cx gates in the entanglement layer with circular entanglement. So you can hear across 3 qubits. So you can see we've got 3 qubits and 2 repetitions. This is what is the Ry and Rz gates in the rotation blocks, and we've got the entanglement blocks with the Cx. We've told it that we want a circular entanglement. And so here is what it looks like. We've got a layer of Y rotations, we've got a layer of RZ rotations, and then we've got circular entanglement using CX gates. And we've got it twice with the final layer of rotation gates. So since the n-local is a more general version of the 2-local circuit, so here is the equivalent n-local circuit. So you can see here we've still got 3 qubits and 2 repetitions, but we define the rotation block slightly differently as well as the entanglement block. But you can see that we end up with the same circuit. But of course, using the n-local function, we can create more complicated parameterized circuits. So here you can have a rotation block based around 2 qubits, an entanglement based on 4 qubits, and then we're going to use linear entanglement. So here is that in the Qiskit code, and this is what it looks like. So we're using an entanglement block which is a Y gate and a Z gate, so you can see them stacked here on these 6 qubits, Ry, Rz, Ry, Rz, Ry, Rz. And then we're doing an entanglement across 4 qubits here. And you can see that that is copied linearly across the 6 qubits with that final rotation layer included. So if we want, we can also create a completely custom parameterized circuit feature map. And to do so, you just create a quantum circuit with a parameter vector. And so here is an example of that. So this is actually very similar to a ZZ feature map, but instead of those Hadamard gates, we've actually just removed the Hadamard gate layer. So let's actually now encode some data using these feature maps. Let's encode the first training sample data point using the ZZ feature map. So this is what that first sampled data point looks like. And here is how we encode it using the ZZ feature map. So first we define the feature map. We have 4 dimensions. So we define it with 4. We're just going to use 2 repetitions, linear entanglement. And then we take that feature map and then we bind the parameters. So we actually provide the parameters with their values from that particular data point. So that's what this line is doing there. And then we're just going to draw it. So you see, as opposed to in the past, where these gates didn't have particular values associated with them, it just said x0 or x1 or x2. You can see that now there are numbers in those gates. So your first exercise in this lab is going to be encoding this 2-dimensional data point, x equals minus 0.1, 0.2, and I would like you to use the ZZ feature map with 4 repetitions. and it's just a default data mapping function. So you should be able to do that given the previous parts of the code given before. So now that we know how to encode the data using a quantum feature map, a quantum feature map naturally gives rise to a quantum kernel, which can be seen as a measure of similarity. So your kernel function between two different data points is going to be large when those two data points are close in your quantum feature space. When we're considering finite data, we can represent the quantum kernel as a matrix, and we can calculate each element of this kernel matrix on a quantum computer by calculating the transition amplitude between one data point and another. So this provides us with the estimate of the quantum kernel matrix, which we can then use in a kernel machine learning algorithm, such as support vector classification. So we're going to be stepping through how to do this fairly slowly. Just a couple of theoretical points first. So as discussed in that Nature paper I mentioned earlier, quantum kernel machine learning algorithms only have the potential of quantum advantage over classical approaches if the corresponding quantum kernel is hard to estimate classically. But as we will see later, the hardness of estimating the kernel using a classical computer is only a necessary and not always a sufficient condition to obtain quantum advantage. So all that means is that even if the kernel is hard to estimate classically, you still might not get quantum advantage. But it was proven recently in this paper by IBM Quantum that there do exist learning problems for which learners with access to quantum kernel methods have a quantum advantage over all classical learners. So that's really dependent on the data type of problems and the quantum feature maps involved. So with our digits data set ready, we're going to be setting up the Qiskit quantum kernel class with the ZZ feature map, since that is conjectured to be difficult to simulate classically. And we're also going to be using the state vector simulator to estimate the training and testing kernel matrices. So here is the Python code required to define our ZZ feature map. We're going to be using linear entanglement with true repetitions. And then here is how we define our quantum kernel. We give it the feature map and the backend that we would like to use to create it. So here you could provide a hardware backend or different simulators. So let's calculate the transition amplitude between the first and second data sample. So this is going to be one of the entries in the training kernel matrix. So here is just the printout of those two first data points. You can see they have 4 dimensions. And now we're going to create and draw that circuit. So we take the kernel and then we construct a circuit between that first data point and the second data point. And here I'm just going to draw it with some decomposition so you can see the shape. So you can see that it's fairly long, and if you squint very closely, you'll see a couple of points. So first, the circuit shape is symmetrical. We have a set of Hadamard gates. We have our Z0, our P0, so just the Z gate, and then we have our ZZ part. And then because we've got 2 repetitions, we've got that again. Hadamard gates, Z gates, ZZ gates. And then because we're calculating the transition amplitude between one data point and another, and that is defined as taking the feature map of one data point and then doing the conjugate of the other data point. And in circuit, that means in circuit terms, we actually just need to invert the circuit that encodes that second data point. So that is what starts between these two CNOTs right here. So you might notice that this unitary gate here has a different value in it from this unitary gate here, and that it's because the rest of that circuit is encoding that second data point. And so you can see we've got the ZZ part, we've got the Z part, we've got our Hadamard gates again, we've got our ZZ part and our Z part, our Hadamard gates again, and then our measurements at the end of the circuit. So now we're going to simulate the circuit. We're going to be using the CHASM simulator since the circuit contains measurements, but we're going to increase the number of shots to reduce the effective sampling noise. So here we define our backend, we're going to execute that job and then grab the counts from the result object. And our transition amplitude is just the proportion of counts in the 0 state compared to the rest of the state. So you can see here, we get a fairly small count of this number here, 0.0019, or just really rounded up is 0.002. So this process is actually repeated for each pair of training data samples to fill in the training kernel matrix. And then it's calculated between each training data point and each testing data point to fill in the kernel matrix, the testing kernel matrix. Note that each matrix is symmetric because the transition amplitude from, let's say, data point X to data point Y should be the same as the transition amplitude between Y and X. Apologies for the coughing fits. I have a bit of a cold at the moment. So note that since each matrix is symmetric, to reduce computational time, the Qiskit code actually only calculates half of the entries and then just reflects the matrix, copies and pastes the entries into the other triangular part of the matrix. So here is the code to compute and plot the training and testing kernel matrices. So here we grab that kernel and we evaluate the matrix given the training data. So note if you don't give a Y vector to the kernel matrix, it will calculate itself in a product. And then if we want to calculate the testing kernel matrix between two different sets of data points, we give it a Y vector and a X vector, test and train. So looking here at the matrices themselves, what do we notice? Well, first, the training kernel matrix is square, and that is good because we're calculating the distance or the measure of similarity between every data point and itself. Every data point in the training data set with every other. And you might also note that we have a diagonal of 1, and that's because we're measuring the similarity of the data point with itself, which we hope would definitely be 1. And so you see in the testing kernel matrix, we're calculating the similarity between every training data point, of which we have 100, and every test data point, of which we have 20. Hence the rectangular shape. So now this leads me to our second exercise of this lab, found quantum kernels. So we're going to be asking you to calculate the transition amplitude between the X that we encoded earlier and this Y data point, 0.1 and minus 0.6. We're going to be using the feature map that we prepared earlier. So the feature map for repetitions default mapping data mapping function. Going to be asking you to use specific numbers of shots and seeds for the QASM simulator, just so that the circuits are comparable. You should be able to do this based on the code prepared earlier. So, moving on now to quantum support vector classification. So this was introduced in that Nature paper mentioned earlier. The quantum support vector classification algorithm consists of these steps. First, we're building the training and testing quantum kernel matrices. So as we saw just previously, our training matrix is for each pair of data points in the training dataset, we apply the feature map and measure the transition probability. And then our testing quantum kernel matrix is for between every training data point and every testing data point, we apply the feature map and measure the transition probability. And then we use those quantum kernel matrices in a classical support vector machine classification algorithm. So what does this actually look like? Well, we're going to be using the scikit-learn support vector classification algorithm, SVC, and this actually allows us to find a custom kernel in two different ways. We can either provide the kernel as a callable function, or we can pre-compute the kernel matrix, and we can do either of these using the quantum kernel class in Qiskit. So first, we're just going to be grabbing those training and testing kernel matrices we calculated earlier, and then give them to the scikit-learn SVC algorithm. So we set it up saying that we're going to be giving it a pre-computed kernel, and then we provide it with the training matrix, with the training labels for training, and then we score it by giving the test matrix and the test labels. And you can see here that we get a test score of 95%. So here we give the kernel as a callable function. So we set up the SVC algorithm and we tell it that the kernel we want to use is from this, this particular function of the quantum kernel class. And we want to fit the data points sample, the training sample with the labels. And then we want to score again the testing samples. And luckily, since it is the same code calculating the transition probabilities. And here we were using the state vector simulator, so we don't even have any sampling noise. We can see that we get the same score. So giving the code, giving SVC, the algorithm, the kernel as a callable function is actually quite convenient, because what we can do at the same time is we can easily compare the quantum kernel with various classical kernels. So here, scikit-learn has 4 or so predefined classical kernels. We've got a linear kernel, we've got a polynomial kernel, we've got a radial basis function kernel, and we've got a sigmoid kernel. So here this code just loops over these 4 kernels and applies the classification algorithm on them, using them, and then scoring the test ones. And you can see that the classical algorithms perform at the same accuracy or even better than the quantum kernel. So this is what I meant by earlier saying that just because we're using a quantum kernel that is difficult to simulate classically doesn't mean we're going to be getting advantage for our particular data set or our particular problem using a quantum kernel. So yeah, as further exploration after this lab, why don't we all try running quantum support vector classification with different Qiskit feature maps. You can make your own using 2local or nlocal, and you can also play around with different data sets. There's the WINE or the IRIS or the PRESC breast cancer data set, or you can even try to differentiate between the different numbers in the digits data set. You can also play around with reducing the number of dimensions and features from the 64 to 2, 4, 8. And of course, when we're doing this, the data sets that we think we may get advantage in are those which are more close to the quantum feature map that we are using. And I believe this probably would have been discussed in the previous lectures. So thank you very much and good luck with the exercises and this exploration.